Hey everyone. So I want to show you today a technique called latent semantic analysis. And what I'm going to do is I'm going to show you how we can mine concepts from a collection of documents. Um, my goal here is to give you a reason why to do TF-IDF. So we talked about TF-IDF. We're probably going to do more TF-IDF later on in class. But we haven't covered much machine learning yet. We haven't covered a lot of the models that we're going to build. So I want to show you just a quick, easy way to make TF-IDF useful. All right, so I'm going to be doing some analysis on the forum posts from week 0. So if you remember in week 0, I asked everyone to go post on our forum, what is your definition of data science after having watched Josh Wills and Hillary Mason's videos? Okay, so you did that. I downloaded that data into an XML file, and I'm going to use this program to parse it. And so what I'm going to do is I'm going to open all of the entire XML file just into a great big blob. And I'm going to use this thing in Python called Beautiful Soup, and Beautiful Soup is really good for parsing XML and for HTML. And what I'm going to do is I've gone in and I've found that all of the posts that are in the raw XML are wrapped in text tags. So then what I'm going to do is I'm going to use Beautiful Soup to find all the text tags, and what I'm going to get is I'm going to get a list of documents, and I'm going to do a little bit of cleanup on them. And so now I have a corpus of documents that where each document is your posts from week 0. Okay, before I get into a lot of the TF-IDF vectorizing, I want to introduce you to a concept that you haven't probably heard yet, and it's stop words. And so stop words are words that I don't want to convert into features because they're just not especially useful. So words like a and the, I don't even need to consider these words. So I'm just going to throw them out. And also using stop words gives me the opportunity to filter any junk that's in the data. And in this case, there's a lot of HTML junk that's left over from the download. And I'm going to clean that out too. So my initial set of stop words is going to come from stopwords.words English, and this is part of NLTK, which is the Python Natural Language Toolkit. And I'm going to add these words to it as well, and these are all a collection of HTML junk that I didn't want in my analysis, and I found these as remnants by just kind of going through the data. All right, so now that we have a list of documents, a corpus of documents, I'm going to want to convert them with TF-IDF vectorizing. Here's an example of the very first element in my list, so the very first document, and this is one of the posts. And you can see there's some of that HTML junk still left over. All right, instead of writing my own TF-IDF vectorizer like I did last time, I'm going to use the TF-IDF vectorizer that comes with scikit-learn. It's much easier. I'm right here using stop set, which I defined above as my stop words, words to throw out. Use IDF equals true. You don't have to use IDFs, but it's definitely going to be a good idea here. N-gram range is pretty interesting because what this lets us do is look at not only tokenized by single words, but we could also look at bigrams, which is occurrences of 2 words, and trigrams, occurrences of 3 words. And we're going to look at all of those. And there could be 2 words that occur together that could be important, or 3 words that occur together that could be important. So we're going to look at all of those. And so X, whenever you see an uppercase X like this, you can assume that this means a matrix, as opposed to if it were a lowercase x, it would probably mean a vector or just a single variable. That's just by convention. That's how machine learning people tend to work. So X is going to be our input set. It is going to be a matrix, and we're going to call fit transform on the set of documents, the corpus. And then what we can see is x0, which is the transformed first document in the corpus, transformed to TF-IDF, is going to be a row vector sparse matrix of 3,393 elements with 89 stored elements. Okay, what the heck does that mean? I just sprung a bunch of stuff on you. All right. If you remember back from our last example, we saw that when we used TF-IDF, what happened is all of the unimportant words, or the words that didn't occur across that occurred commonly across everything, they just kind of washed out to zero. Well, also we saw that there could be many documents or many words that occurred in one document in the corpus that don't occur in document 0. And so they wouldn't have a score associated with them because they don't exist. So a sparse matrix is a really handy way to save some memory by only storing the elements that do exist and have a score. So we can see, and I'll print document 0 here in its sparse matrix form, and what you can see is that even though there are 3,393 elements in the matrix, well, in the array in this case, really we only score 89 of them, and here they are. So this is going to be 0 by 647, so this could be interpreted as the 647th word, and this would be its TF-IDF score. Not to worry, though. I know that probably seems confusing, but it's going to all be handled for us by scikit-learn and by Python. Okay. So now we have a corpus of TF-IDF transformed documents. Great. Here comes the LSA part, latent semantic analysis. What we're going to do is we're going to take X, which is our matrix, our input matrix, where M is the number of documents and N is the number of terms. So imagine a document by term matrix. And I'm going to take that matrix and I'm going to decompose it into 3 matrices called U, S, and T. And when we do this decomposition, we have to pick a value K, and that's how many concepts we're going to keep. In this case, I chose 27 because I wanted to keep as many as there were documents, but that's an arbitrary number. Okay, and so what happens is X, when we decompose this matrix X, what we get is 3 matrices, U, S, and V transpose, that when multiplied together approximately equal X. If you've never seen matrix decomposition, that's okay. You really don't need to know anything more than I just said. What we do is we solve for 3 matrices that more or less multiply to be X. Good enough. Okay, there's some important things that happen, and I won't get too deep into the math on why they happen. But what happens is U will be an M by K matrix where the rows will be the documents and the columns will be mathematical concepts. That's kind of weird to think about, but what we're going to learn are concepts that were contained within the documents. S is going to be a diagonal matrix, and the elements will be the amount of variation captured from each concept. And then V is going to be an M by K matrix, watch the transpose, where the rows will be the terms and the columns will be the concepts. So now this is going to be a term by concept matrix. And this is the one that we're actually going to be the most interested in because we're going to want to understand which terms comprise a concept or which terms can be used to describe a concept. Because concepts are a mathematical construct and they don't really have word labels. Okay, so just as a reminder, the shape of X is 27 documents by 3,393 terms. And the reason there's so many is because it not only counts the single terms, but also the bigrams and trigrams. All right. So what we're going to do is we're going to instantiate an instance of truncated SVD, that's truncated singular value decomposition, which is the engine I'm going to use to decompose my matrix. And by calling lsa.fit on my matrix, I'm going to decompose it. We can see that's happened. And This thing called lsa.components underscore is what gets created, and it represents V, which is the term by concept matrix. And so if I look at 0, what I'll see are these are all of the terms that go with concept 0. All right, well, so that doesn't really help me. It's just a bunch of numbers. How do we know what terms those are? Okay, well, so the first important thing to know is these are the importances, or the how important that term is to that concept. And the position, 0, 1, 2, 3, 4, and so on, relates to the position of the term. So I can get a list of all of the terms in that same order by calling vectorizer, which is my TF-IDF vectorizer, .get feature names, and that will give me a list of the terms. And then what I can do is for each of those components, I can go through them and I can take the terms and stick them to the importances, the component to the concept importance, and then I can sort them. And I'm going to only print the first 10 terms, so the first 10 terms that make them up. And then here we go. All right, so when I run that loop, what you'll see is concept 0. All right, concept 0 has these as the most important words. Data, procedures, that doesn't tell us much, but look at this, large amounts of data, large amounts of data. So this is really that concept. LSA has identified here that concept of big data, large amounts of data. It's something that almost all of you wrote about, and the concept was identified here as across all of your documents, something that's important. All right, concept number 1. There's some data science. Those are words that we used a lot, but answers and decisions, questions, findings. So finding the answers, making decisions, answering questions. That's really what we're talking about in concept 1. Concept 3 is an interesting one here too. If you notice, I skipped concept 2 because it looked kind of like it had quite a bit of junk in it. Things that I didn't filter out quite as well as I should have. Excuse me for that. So let's move on to concept 3. Concept 3, here we can see we're make better decisions, use good, better, make better, use data, right? So we're using data science to make better decisions. That's pretty awesome. We identified that. So what do we have so far? We have making better decisions, using big data, and finding answers to questions. Let me write those down just right below. So using big data, making better decisions, answering questions. All right, I think that's good. Next one. So analyzing information, that in creative thinking and science. I like that. Those are all good. Creative thinking, analyzing information. Those are two pretty different things, but they're kind of conceptually the same to the computer. And then this next one's about data science and data scientists, and it also captured the idea that someone had used about data science compared to archaeology in history, and I like that too. And so I can go on and on, but what you can see here is that the computer has started to piece together some concepts that kind of come up with an average conceptual idea of what data science is based on your posts. And I don't know what you think about that, but I think that's pretty cool. If you think that's cool too, let me know. Post about it in the forums. And also, you're going to have some homework that looks a lot like this, and I'll have that up shortly. Thanks a lot. Bye.